this will be the wrap-up mini lecture to Chapter 16 NMR stuff. We will return to Chapter 16 and learn a little bit more about mass spec later on in the semester, a little bit later on in the semester. So, little recap as usual. What do we know how to do at this point? Basically, we can look at it two ways. If I have a structure that I'm looking at in front of me, I can predict the number of sets of chemical shift equivalent nuclei, aka homotopic nuclei. I can use my correlation chart to predict the approximate chemical shift for each set. And then for proton NMR, this is all proton NMR, look at the splitting pattern that I would predict for each of those sets of hydrogens based on the n+1 rule. Now, I also know how to use integrals to figure out how many hydrogens are associated with a particular signal in the proton NMR. And given a proton NMR spectrum, I should be able to analyze it and pull it all together to figure out what structure is actually giving me this particular spectrum. It's a lot. So why don't we just stop here? Because most of the stuff that we see in reality is not that simple. So for example, there are a lot more complicated splitting patterns in proton NMR. And Carty goes through an excellent example toward the end of the chapter, talking about bromoethane, where he reveals, and we've talked about in class, the fact that that hydrogen is not the same as that hydrogen, and that's not the same as this hydrogen. They're all uniquely heterotopic hydrogens. Oof. And that leads to very complex splitting. So he went through bromoethane. I'm going to go through a molecule called vinyl acetate right there. So again, we've got H sub A, H sub E, and H sub C. How do we know what this spectrum will look like? Well, here's the spectrum, and some of it's really straightforward. Like the signal at about 2.2 is very obviously the methyl group on the ester. But here we can certainly see 1, 2, 3 sets of signals for the 3 vinyl hydrogens. Wow, pretty broad range here. That one down around 7.4 is very far downfield. Let's analyze this. So, key information to know is the coupling constant. That's what's going to allow us to figure out which hydrogen is giving which signal. So, since we know each of those 3 vinyl hydrogens is heterotopic, and we can see that they're neighbors, they should couple one another. And the coupling between these 2 hydrogens that are trans to one another is 15 Hertz. The coupling for the 2 heterotopic hydrogens that are cis to one another is smaller, 10 Hertz. And these two, well, you know what? They're not neighbors, they're both on the same carbon. That's called geminal coupling. The point is, H sub A and H sub B here, they are heterotopic. So they couple with one another, and the coupling is pretty small. It's usually around 0 to 2 Hertz. So with that information, we should be able to construct a tree diagram and analyze the spectrum. So here's the quite detailed tree diagram. So if I'm looking at all 3 of these hydrogens, 1, 2, and 3, we'll start at the one at 7.27, the one that's furthest downfield first. Alright, so that's this guy right here. It is split into a doublet. We'll go over here. These 2 couple with one another at a pretty big trans coupling. we said that was around 14 hertz, and in fact it was measured in the spectrum and it's 14.2. So we start out by drawing that doublet. There's that big doublet from this guy coupling to this guy. But now we also know that this guy couples to this guy. And that's a cis coupling, and that was around 10 hertz. And so each one of these signals is then split again with a smaller coupling. In fact, that coupling is not even as big as 10 hertz. It's around, according to this, it's 6.5 hertz. So what we end up with here is a pattern that looks like this, and it's called a doublet of doublets. Well, you can do that with all of these signals, clearly. So again, now let's look at this guy again. We know it's coupled in a cis fashion to that one. So that's apparently that hydrogen. We know that the coupling constant, the measure of the interaction between those two hydrogens, was 6.5 hertz. So there's our doublet. But now we also know that this guy is coupled in a geminal fashion to the yellow circled hydrogen. Now that's the one that's a really tiny coupling constant. So that's revealed right here. Little teeny 1.2 hertz. So while my doublet of doublets on the far left, furthest downfield, looks like this, a big old gap and then a big old gap. Over here on the far right at 4.57, it's a little teeny gap, big gap, and then a little teeny gap. So we can do that for all three of these hydrogens, and then we'll just pull it all together and show you the tree diagram superimposed on top of the spectrum, and you can see that in fact they really do reflect what we were, plotting out in the tree diagram. So here's the furthest downfield hydrogen that has both the large trans coupling and the pretty large cis coupling, and here it is. Here's the coupling constant from that cis coupling, and then if you go right into the middle here, that gives you the trans coupling. Well, that same trans coupling is evident right here in the middle hydrogen, if you will. And there's the teensy-weensy geminal coupling. And then finally, we can point out this guy. Again, the tiny gap, the 1.2 hertz gap for the geminal coupling, and the larger cis coupling constant as evidence from the middle of each of those two doublets. So all three of these are known as doublets of doublets. And note that they are truly doublets. They're all equal height. And that is how you analyze these particular complex examples. All right, so if I completely ignore this, and I don't know what this is, when I get the spectrum, what I'm going to do is I'm going to blow up the peaks, and I'm going to figure out the coupling constants, and I'm going to say, oh, this coupling constant is around 14? Ha! I know that trans coupling is around 14. I must have trans coupling here. So it's really complicated, and this is not the sort of example you'd ever have on an exam, but homework is a reasonable possibility. All right, another example of complex splitting is the fact that the n+1 rule only applies, well, let's be strict, when we use the N+1 rule, N means homatopic hydrogens. So, when I start looking at those CH2 groups on these two examples, you're absolutely tempted to go, well, gee, there's 3 hydrogen neighbors here, there's 2 hydrogen neighbors there, 5 plus 1 equals 6. 2 plus 3 is 5 equals 6. But neither of these are sextets, because if it was a true sextet, there would have to be 5 chemical shift equivalent hydrogens. And the CH2 and the CH3 in each of these examples, they're not chemical shift equivalent. So what's going on? Well, let's look at one of these CH2 examples. We'll construct a tree diagram. So the first thing I'm going to do is look at the splitting by the neighboring methyl group. That CH2 has a neighboring methyl, so that will split its signal into a quartet. Now, this is typical vicinal coupling, plain old-fashioned N+1 type of coupling between next door neighbors, so that's going to be around 7 Hertz. But now, in addition to the CH2, we also have next door neighbor vicinal coupling from the CH2. I think I said CH3 before. Okay, so we've got the quartet arising from vicinal coupling with the CH3. Now we look at the CH2 to the right on the top example. This means each one of these signals is further split into a triplet. Okay, so the green coupling is reflective of the CH2-CH2. The blue coupling is the CH2-CH3. And basically, what happens is each one of those quartet signals gets split into a triplet. So, how do I get a 6-line pattern out of that? Well, that's the thing. If you look carefully at this particular tree diagram, you can see that it's going to look like a 1 to 3 to 1, 2, 3, 4 to 4 to 3 to 1 pattern, because all 3 of those are right on top of one another. All 1, 2, 3, 4 of these are right on top of one another. Why? Because it's essentially the same coupling constant. So you end up with what, for all intents and purposes, looks like a perfectly happy sextet. 1, 2, 3, 4, 5, 6. But it's not a sextet. It is a quartet of triplets. Okay, so that's what it really is, although you'll see in Cardy and other textbooks they'll often call it a sextet. It's not a sextet, it's an overlapping quartet of triplets. Whew, who needs this? Well, it's really, really important when you're trying to elucidate the structures of complex molecules. Now, another example of complex splitting? Aromatics, UFTA. So, when are these hydrogens not chemical shift equivalent? Well, so let's put a R group here. If we have an R group here, then this hydrogen is meta to the R group, this hydrogen is para to the R group. They are not chemical shift equivalent. They will couple with one another to the tune of 6 to 10 Hertz. How about these two? Again, ortho versus para. These two will couple. They will split each other to the tune of 1 to 3 Hertz, and even hydrogens that are as far away from each other as para can couple, although the coupling constant is really quite small. So in this particular example, we've got a bromonitrotoluene of some description. Here are our aromatic hydrogens. And we've got 3 hydrogens. By analyzing this NMR spectrum carefully, we should be able to assign all three of these hydrogens. This is a doublet, this is a doublet of doublets, this is a doublet. So this is a great homework problem. You just might see it because I like it so much. But again, on a quiz or an exam, the really easy stuff is to recognize that for para-substituted aromatics, you invariably get this funky looking pattern that's totally symmetric, and it really looks like, almost looks like a quartet that got a big gap in the middle. And sometimes, in fact, these kinds of patterns do look a lot closer to a quartet. This is a dead giveaway for a para-substituted aromatic ring. So when you see this nice symmetric pattern that kind of looks like two doublets or a quartet, obviously equal integrals, that's saying, boy oh boy, that's definitely a para-substituted aromatic. Okay, bells and whistles for that. Alright, I know you really want me to stop by now. I can't. There's one more thing we need to talk about, and that's stereochemistry. So if I was looking at this, what do we got here? A 1, 2, 3, 4, 5, 2 pentanol. So a 3-methyl-2-pentanol. Well, if I was going to take a C13 to that, C13 is easy. 1, 2, 3, 4, 5, 6. I should expect 6 signals, right? Sure, why not? Well, there's my C13 for this molecule. How many signals do I have? 1, 2, 3, 4, 5, 6, 7, and I can't even tell. That might be 2. So I have at least 7 signals, maybe 8. What in the heck is the deal here? Well, what the heck in the deal is here is stereochemistry. We're looking at the carbon nucleus right now, and so I ask you, is that carbon in the same identical electronic environment as this one? This guy versus this guy. And the answer, of course, is no. This carbon is on the same side of the extended carbon chain, whereas this one is on the opposite side of the hydroxyl. So what we're looking at here in this C13 is a racemic mixture, eGads, and so we are seeing what is known as diastereotopic carbons. I'm just letting you know to be aware of complex NMR spectra. The proton NMR spectrum for this molecule is even worse. As you can see, it's just a hairy mess because of this stereocenter and this stereocenter. Hiawatha. Nothing's ever easy. But bad jokes are really easy. So what's this? Give up? Well, this, I'll give you a big hint here. This is saline, right? Salt dissolved in water, maybe. Saline, saline over the 7 seas. Okay, that wraps up NMR. We'll see you in class.